Hey, hello. This is the recording session, solo recording session for magnetic induction. This is the very last topic to speed run. We have done it. You have done it. Rather, I have done it. We're at the end. Okay, so if you've been speed running with me, take a deep breath. And we are at the last chapter of magnetic induction. Okay, all the other chapters are covered in various format or video. Of course, it's not a complete coverage, but I think it's a good enough coverage to get you set up for your exam. All right. So in chapter 22, if you watch the previous video, we talk about how basically the main idea of magnetic force, which is current inside magnetic field where the outcome is force. Okay, so when it comes to electromagnetic induction or your Fleming's right hand rule, it is different because in this case we are talking about current being the outcome. So you have a moving conductor in a magnetic field, for example, a dynamo, because it is spinning. Okay, and the outcome is induced current or induced EMF. Okay, so here we're going to start off this topic is like two laws to rule them all. So the first law that we talk about is Faraday's principle or Faraday's law. And Faraday's law says that the induced EMF in a closed loop is directly proportional to the rate of change of magnetic flux linkage. You're right, magnetic flux is also good enough. So magnetic flux linkage, the symbol is phi. Okay, so whenever we're gonna break this down a bit. Okay, so the first thing we look at is we need to have a closed loop. So this is the condition. Okay, and what is happening here is we will have an induced EMF and it is directly proportional to magnetic flux rate of change. Okay, so we put in the equation, we will have induced EMF E is directly proportional to the flux dt. Okay, before I break this down, I also want to tell you that there's a negative sign here, but you may be thinking, why is there a negative sign? Okay, so the reason why there is a negative sign, teacher ask, teacher answer, is because, number two, we also need to talk about Lenz law, which is the law of opposition. Okay, so when there is a change in magnetic flux, the induced current will flow, or the induced EMF will flow in such a way as to oppose. We're going to oppose the changes. Okay, so this opposing the change, we represent it in this negative. Okay, so before we start any of this, we need to be able to know what on earth is flux. Okay, so flux is equal to NBA. Okay, NBA if theta is 0. So I'm gonna just give you drawings. Okay, give me a sec to pull out the drawing. Okay, so your theta has to be 0. So your magnetic flux linkage, if you remember your notes, let me define it, will look something like this. Okay, so this area must be 90 degree. If it's not 90, then we will use sine theta, where theta is between the plane and the angle. So this is how you define magnetic flux law. It's the product of BA. Magnetic flux is this one. This is magnetic flux. Hang on, let me write. Change the notes first a bit. Ding, ding, ding. Push down a bit. Okay, so this one is BA, is magnetic flux. One turn in your coil. NBA, these two. NBA or NBA sine theta, the National Basketball Association. This will be magnetic flux linkage. That's why they call this N flux. Okay, so don't be too hung up on this. Whenever there are multiple terms, we just multiply by how many terms there are. Turns. Okay. So right now, we understand that if you want current to be created inside this coil, which is the whole idea of induced EMF, which is the reason why you even have electricity in the first place, something is changing the magnetic flux in the circuits in your house. Okay, so what causes that change in magnetic flux? You have so many options. Okay, so I'm just going to put a list here to change the magnetic flux. Option 1, look at the equation. We can change theta. There, NBA sine theta. Change theta law means we can rotate the coil. When you rotate the coil, you change the flux. Okay. Option number 2, what else can we do? We could change the area. Ah, yes. But how do we change area? We change area by moving either coil or magnet like this. So I think I've discussed this example with you before, where there is an area with magnetic field. Okay, maybe this is the area where you have your magnetic field going into or out of the page. It doesn't really matter. Insert the rod. It doesn't matter. Okay, so let's say you have a changing magnetic field. It will affect the direction of the current. Okay, so maybe your coil is like, wee, go inside. So it's like chip small. Or here no EMF. Okay, and then after that, sorry, no magnetic flux. And then when you reach here, you got half magnetic flux. When you reach here, you have full magnetic flux. So you can see the area where there's magnetic flux is actually changing from none to full. Go and watch the video. I have recorded a long video to explain this. Filled with teaching aids such as masking tape and etc. Okay, so you can change area. All right. Number 3. What else can we change? We could also change. Why you don't let me change my pen color? Okay, never mind. We can also change the okay, we got A. We can change B. And the way we change B is by turning on or off the switch. Let's say you have a circuit, you can turn on and turn off the switch. Or the current in the solenoid that creates the magnetic field. Okay, you could move coils closer or further away from each other. Okay, you could put alternating current in the coil. So there are many ways to change the magnetic field. So this one is normally from the perspective of mutual inductance. Or this one, mutual inductance. Mutual inductance situation would look probably something like this. Okay, you can watch the video. We have recorded a full-on explanation. It also came out in your trial paper 5. We use a changing current in one coil to disturb the flux in the other coil. Whoops. Like this. Okay, so this is your changing. You can change this current by changing this current. You can turn on, turn off this current. You can move this coil closer to each other, or you can just change current however you want. So it's either alternating current or varying the current. Okay, so we are at BA theta. Oh, Miss got N. N got, but that N would look a lot like transformer. Okay, so in the perspective of N is using transformer. So transformer is a direct application of mutual inductance, meaning to say you should be able to explain what causes a transformer in the first place. Okay, so you can watch the explanation that we have recorded from ON12 paper 41. This is a transformer. So we talk about how a current gives rise to induced EMF. This is very important. Don't have transformer, then you probably won't have your laptop, my PC. None of this will happen. You will learn physics by reading textbook already. Okay, so a transformer changes the input current to an output current, and the reason why we want transformer is because if you again look at what we've discussed in chapter 24, I didn't really cover this because the videos are pretty good, so please go and watch the video. It's a very important idea where whenever we send current from a power plant, we step up, we step down. So basically as humans, right, we have managed to master electricity by mastering magnets. These are very big ideas, okay? But what you need to know for exam are things like, for example, why is the core made out of iron? To increase the flux linkage so that we can link them carefully. Okay, and it's easily magnetized and demagnetized. Why is it laminated? This is to reduce energy loss due to eddy current in the core. So you can see when we have a laminated core, there is no, because in between we put some insulator, so there's no space for the eddy current to build up because the electron cannot transfer to another layer. Okay, so normally when you try to explain why is there an induced EMF, you must mention what causes the change in flux. So for example, in this case, there's an alternating current in the primary coil that causes a change in magnetic flux in the core. And because the core is linked to the secondary coil, because they are bounded this way, okay, so there is a changing flux in the secondary coil, induces the EMF in the secondary coil to oppose the change that caused it. Lenz law. Okay, so it's a bit like, hello, my name is primary coil and I have changing current, so I have changing flux. Hello, my name is laminated soft iron core, and because of me, you are tied together. Secondary coil then responds, you change my flux, I don't like it, I create or I induce EMF to oppose. And by energy conversion, because you have now electricity, this thing will become hot. Okay, and we try to reduce eddy current by laminating the soft iron core because in that sense, then there's no place to build up, not much space to build up eddy current. Okay, so all of these transformer, you should check out some questions. I'm just going to list down the ones that we have recorded for you. So you can go and find in the playlist ON12 paper 41, question 7. Also, don't forget to check out the alternating current ones that we have also recorded. And also there's a long form explanation there for you. Okay, so that would be, let me bring it in. These are all the transformer questions. Okay, so either you watch them or you go and try them. Okay, so transformer, normally it comes together with Lenz law. So there is nothing else to teach in this topic because we are going to apply ideas of how changes in flux causes an induced EMF, and we should be able to explain, describe, sketch, calculate. So the key skill, the skills that we are looking for in any various combination, number one, is explain using the laws. Lenz and Faraday. Step 2, calculate. And this calculate can be using EMF is equal to the flux dt, or calculate based on a given graph. Okay, so normally they will ask you to find the gradient of flux against time. Okay, could be magnetic field against time. Why? Because from here to here, flux is proportional to magnetic field. No, flux is BA. Or it could be gradient of current against time. Why? Because from here to here, magnetic field is proportional to current. Remember, in the very beginning of your magnetic field recap, I did mention that, hey, this is important. This is important. And then this is proportional to this. Okay, so there's some form of calculation. They can give you a graph that you need to analyze. And if they give you a graph that you need to analyze, they could also give you some values or some situation where you have to sketch induced EMF. Okay, so when you explain, we are going to try to go through these skills. And number 4, we are going to test whether you know the difference between induced EMF versus Hall voltage. They are not the same thing. So these are the skills that they will test. So make sure if you are doing revision, you cover at least 1 or 2 questions from each aspect. Okay, I will try my best to do questions that will test a big variant. Okay, so let me go and hunt now. And generally the questions are all different, especially the explaining ones. So yeah, that's why sometimes people can find this topic a wee bit challenging. But for people who like to think and don't like to memorize, and this is like very nice. I just need to get the idea and understand it and know how to apply it, then I'm set. Nothing much to memorize. Very nice, very nice. Okay, let's look at this. The 20, paper 42, question 9. Drop this. Oops, my mouse, hello. Okay, so in this case, you have a standard setup of a solenoid and a small coil placed at the solenoid. And you can see in this case that we have a scenario where the current will change with time. Sure. So basically what is happening here is turn on the switch at T1, then you turn off the switch at around T2. That is just legit what is happening. Anyway, after they ask you to define Faraday's law, you are then, and it's very nice one when they ask you to sketch. I prefer to sketch than explain. It's 4 marks, man. If it's a 4 mark explain, then I will have a headache. Anyway, this one is actually testing whether you can sketch the graph, and lo and behold, whether you can differentiate this with your Hall probe. Okay, so I'm going to start from the top. Okay, so again, this question is from Winter 20, paper 42, question 9. Okay, small coil is placed close to one end of a solenoid connected to a power supply. The plane of the small coil is normal to the axis of the solenoid as illustrated. Power supply causes the current in the solenoid to change with time t. Okay, boss, so the current will 0, 0, 0, 0, 0, increase, maximum, 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 decrease. Okay, turn on the switch, turn off the switch. State Faraday's law of electromagnetic induction, 2 marks. Okay, so the law here says that the induced EMF is directly proportional to the rate of change of magnetic flux. H in a closed loop. 2 marks. At least you should be able to write the definition even if you don't really intend to answer this topic, because it's kind of bonus. Okay, whoa, bruh, need you the whole thing. Okay, there we go. Okay, so where are the marks? I'm looking at the mark scheme now. If you see directly proportional, induced, wow, they're very nice this year. Anyway, Induced EMF directly proportional is one. But direct proportional was such a hanging one. Rate of change of magnetic flux linkage. This is A1. This is M1. So the M1 stops at rate. Maybe students will write rate of change of something else. Okay, so that is M1. EMF induced is directly proportional to rate. And A1 here is when you mention that it is the change of magnetic flux linkage. In other words, EMF is directly proportional to d flux dt. If you write equal, you will get 0. Okay, so it's not equal, it is directly proportional. Okay, sketch how the EMF is induced. Okay, where is there change? Because we know this induced EMF induced in the small coil, this E is proportional to the flux dt, which means this one, flux is NBA. So flux is proportional to B because the number of turns of the coil and the area of the coil is the same. Okay, and B is proportional to I because the current causes the magnetic field in the first place. Okay, so because of this, you go and look at the notes where I provide the equation. B is mu naught Ni over L for the solenoid. Okay, so anyway, here we're going to see that here the gradient is 0. So there's no change in flux. Current is the same, no change in flux. The flux dt is 0, EMF is 0. So EMF is 0 until one box before T1. Okay, boss, let me make this thicker so we can see. It's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, until one box before T1. Okay, and then it is still going to be constant here, one box after T1. So this entire portion here, right, the flux is still the same. I know it increased and it's not 0, but the current is still constant. So the IDT is still 0. And in fact, here also the IDT is 0, but this one is half a box. CRE is such a pain in the head. Okay, never mind. Half a box, 2 box, sure, no problem. 0 all the way to half a box. And then from half a box onwards, it's going to be 0 all the way to the end. All right, so what we're going to do with this one. So I don't know about you, but you see, this gradient is half of this gradient. Because why? Vertically, they change the same amount, but horizontally, for this current, the change is 2 boxes. Whereas for the current going down, the change is half a box, which is 1 box. So this is twice. Meaning to say, this line here, the di dt at T1 is equal to half. This one is a bigger di dt, but you cannot see because I'm writing here. Okay, let me rewrite. Okay, so for this part here, the flux dt, which is also the di dt at T1, is equal to half the gradient at T2. Okay, because they increase the same amount, but T1 is twice the time of T2. So they are going to be double. So I'm just going to make my life easy. Okay, and draw this at 5 boxes, 2, 4, 5 here. 1 is positive, 1 increase, 1 decrease. Okay, so if you want to really follow the sign convention, although it is not that important for this point juncture in your life, you can see if this one increase, the EMF actually have to be negative because the gradient is positive. Lenz law, you oppose the change. Okay, 2, 4, 5. Okay, 5. As long as the polarity is opposite, we are okay. Okay, and then T2 must be only one box. So T2 will have to be double, so 10 boxes and half here. Half to half. I'm going to zoom in so you can see. In the exam, can see, miss? Hopefully can lah. Half to half. This is what I mean by, can't I just give you more space? But never mind. I'm not marking. So half to half, like this. Okay, and then this one is 2 boxes. Okay, so this is the mark for 4 marks. All right, so here is the mark scheme. I'm just gonna provide it for you to learn to check your own answer. EMF is equal to 0 except thin pulses at T1 and T2. Rectangular pulses, some students like to ask me, Miss, I draw dotted line or full line. Doesn't matter. Okay, so T1 is 2 small square. You want to draw full line, I draw for you. Full line. T1 is 2 small square and T2 is half a small square. You got ruler, okay? You don't draw double line like me. Okay, half a small square. They have opposite polarity. And then T2 is double T1. Okay, so cool. This sketching is very popular. Make sure you now sketch. A lot of past year. Go watch, go try. Okay, now a small coil in A is replaced by a Hall probe. Okay, here I'm going to compare for don't know how many times the difference between induced EMF and Hall voltage. The unit is the same lah. Of course, induced EMF, the unit is volt. Hall voltage, the unit is volt. Okay, but this one normally we give it a H. Can this one normally we give E lah, but the units are the same. But we're not really thinking about the similarities. We're talking about the differences. For this induced EMF to exist, there must be a change in magnetic flux. And for there to be a change in magnetic flux, there will be a change in B. And for there to be a change in B, normally there's a change in current. Normally lah, I don't know. Depends, see the question. In this case, yes, we are changing the current. You see, we change the current. Ooh. So whenever the current changes at here, increase, decrease, then there you have EMF here, here and here. Other places, no EMF. Very sad, okay? But what about the Hall voltage? Hall voltage will exist as long as there is magnetic flux density. Don't care whether it change or don't change. Got magnetic flux, got Hall voltage. No magnetic flux, no Hall voltage, because Hall voltage is proportional to B. Induced EMF is proportional to dB dt, assuming all the other things are constant lah, like number of turns and area and theta. Whereas Hall voltage is proportional to B. Not the same thing. I hope you know what the difference is. Okay. So in this case, if I look at this one and I want to draw the variation of VH, you just need to ask yourself, is there a magnetic field? If there's magnetic field, there's reading. If there's no magnetic field, there's no reading. That's all. So I guess there will be magnetic field if there is current. So where is there current? Current will begin to start here and go to maximum here. It really doesn't matter what the value is. We're just looking for the shape, okay? Let me zoom in a bit. So current will start from, whoa, one node, what happened? Okay, there we go. Is my computer? Let me touch. It feels open. It feels quite cool. Maybe it's a one node problem. Okay, anyway, let's go back. Is there a current? Yes, there'll be a current. All the way here got current until half a box before T2. Wee here. Okay. and then the current will drop to 0 within half a box. So we're going to join here, 1 box before T. Oh my god, my line is so straight. What is this? I cannot. OneNote feels that I'm bashing it. I'm sorry, OneNote, but you are kind of... you're great, but you lag a lot. Take it as constructive criticism, OneNote. You're great, but you lag. Okay, anyway, so this one will decrease. Half a box, way down to this one. So you better make sure in your case during the exam, because they give you a big piece of graph paper, that you honor the boxes. Okay, I know paper 5, you don't plot half a box, but in paper 4, you have to follow. Okay. So here got magnetic field, and then after that no more radio, because here no current ma. No current, no magnetic field. Got current, got magnetic field. Then no current, no magnetic field, all the way to there. Okay. So if you show 0, 0 here, you get 1 mark. I'm just gonna crop. Okay. VH shown as 0 before. So as long as you draw 0 from here to here, 2 square T2 minus, okay, from here to here, you draw 0. You draw already. And then from here to here, you draw 0. And then rise to a non-constant value between what? Between T1 and T2. Ah, okay lah. Between, doesn't matter where between T1 and T2. So you get all these yellow one, you get 1 mark lor. So at least you get the general shape correct, 1 mark. Okay. Change at T2 shown as 2 small square wide, and change T1 2 small square, T2 1 small square. Yes, see, they care about this part, and this half to half. This mark. Okay, this one is 1 mark, but it's pretty easy mark if you ask me. Okay, so this is the sketch. Okay, again, one last time, please know the difference between Hall voltage and induced EMF. There is induced EMF when there is a change. So only at the green section there's induced EMF. There, here, whoops, where's my, here and here, tiny. Because here is where the change happens. Here and here. If there's no change, then there's no induced EMF. Now, all 0. Okay? Hall voltage is to measure magnetic field. If there's magnetic field, there's Hall voltage. So here got current, so here got magnetic field, and then just go up. Follow. Because B is proportional to I. Here for you lah. B proportional to I. So they should have the same shape. Okay, so that's the sketching one. Let's go back to the list of skills. We have sketch, we have differentiate induced EMF and Hall voltage. So now we're going to use the graph to calculate and maybe explain some stuff using laws. Okay, boss. Ken. Let me go hunt for a question. Okay, I'm going to do the other variant from ON20. And I'm going to give you a nice bonus. I will do Feb March 21, because Feb March 21 also tests the first 2 skills. Okay, so ON20 P41 question 9. This is a transformer question. Since the AC review, I didn't discuss transformer. I'm going to discuss it now, lor. Okay, Mo? Okay. I mean, it may feel like there's a lot of things for you to study. It is the case if you are studying either your AS and your A2 at the same time. Why though? Why you do this? Why are you so amazing to try to do this? Such courage, such daring, such bravery. Then take 2 breaths. Relax. Okay, so you're doing something really difficult and it's going to be hard. So just try your best, lor. Okay? Know that I think in the future, it's not so much whether you can regurgitate information. It's more of if you know how to find and how to use and how to learn information when you need them, which is what you are doing right now. Okay, ON20 paper 41 question 9. This is a transformer question. Okay, first you're asked to define the magnetic flux. So my friend, magnetic flux is equal to PA, but you need to mention that PA is normal. Or I guess you could say BA sine theta. So I'm going to just say that this is the product of a magnetic flux density, where the flux is normal to the area. Okay, done. So here is a simple transformer, very nice, primary, secondary coil, standard setup. There's a sinusoidal current, so this is an alternating current in the primary coil. Explain how this current gives rise to an induced EMF in the secondary coil. So you see this shape here, sinusoidal, means the current keep changing. If the current keep changing, there is an induced EMF. Think about the previous question. See, current change then got EMF. So now we change the current sinusoidally, there will be an EMF. So how does this current give rise to induced EMF? So you could say that the sinusoidal increase the font size, guys. Okay, let me. Okay, so we're gonna go sinusoidal. Alternating current. You don't say alternating current also, never mind. Just mention current, changing current. Okay. Creates a changing magnetic flux. Flux in the primary coil, because this sinusoidal current is in the primary coil. Since iron core links the magnetic flux with the secondary, between the primary coil with the secondary coil, with the secondary coil, this gives rise to a changing flux in the secondary coil. What you want. Secondary coil also got changing flux. Hence, EMF is induced. Okay. Why the EMF is not constant? Hiya, the rate of change is not constant, no? The rate of change sinusoidal AC is not constant. Point. Faraday's law states that EMF is directly proportional rate change of flux. Okay. Something like this. I will draw some drawing later for you. Okay, so what we're trying to say is your AC in the primary coil, okay, I'm just going to assume it's AC, okay, it's going to go like this, like this, like this, like this, like this. Your dI dt is not constant. And since flux is proportional to B proportional to I, so because of this, the flux dt also not constant. Okay? We change of flux. Hence, induced EMF is not constant. 2 marks only, okay? If you want to, I can also mention that the rate of change of sinusoidal AC is not constant, and because of this, hence, change of flux is not constant. Faraday's law states that the induced EMF, Faraday's law says that the induced EMF is directly proportional to the rate of change of flux, hence EMF is not constant. So my point is current is not constant, so the flux dt not constant. Induced EMF E is proportional to the flux dt. So because of this, E not constant. The I dt not constant, the flux dt not constant, 1 mark. Okay, from Faraday's law, this one is proportional to this, so this is not constant, 1 mark. Okay, explain why the soft iron core is laminated, because we don't want eddy current. Okay, so this one, the whole idea is it reduces induce eddy currents in the core. Okay, and thus energy or heat loss, making the transformer more efficient. Anytime your circuit is hot, like just now when I touch my computer just to see whether it's hot or not, it legit just means it is inefficiency lah. Okay, so reduces the induced eddy currents in the core, it reduces the energy heat loss in the core, and because of this, our beautiful transformer is more efficient. Okay, so this is a question where it's fully on explanation. They can ask you to calculate, so just for revision's sake, don't forget the ratio of NP to NS will be equal to VP to VS. So now to use the equation, go find out how. Okay, I'm going to move on to Feb March 21. Oi, new question, so fresh, so new. And because this is at the tail end, so imagine you are a student and you are preparing for Feb March 21. So you tried the ON20 papers, you kind of got a hang of it. And then now you are sitting for FM21. And you open the paper, paper 42. And you open the paper. Okay. You're a little bit skeptical. You're not sure whether you'll read it, but you know what? Let's go, boys. Let's go. This A-levels gotta end someday. Okay, so you look at the question and define magnetic flux linkage. Ooh. Ooh, what's the difference between flux and flux linkage? Okay, I'll leave you to think about it as you watch this video as I crop the entire question. And then you look at this one. Wow, the graph is so familiar. Maybe they heard me complaining when I was sketching the induced EMF, so they give more time. The gap is bigger. Okay. And then move on to part C, where you have my. Okay. Well, don't scared. You are not afraid because you are well prepared and you understand that for this chapter, questions can be a total wildcard. You're like, okay, read out later. Okay. Normally, when students see something that they never seen before, it's very normal to feel a bit like you can't do this. But try first lah. Don't know ma. Actually, when they are like lines like this, state and explain. Okay, so we're gonna start from the top again. Find magnetic flux linkage. Okay, so for magnetic flux linkage, right? This one is flux, but times n. So we gotta write the equation now. So this is the product of the number of turns in a coil and so this one is also NBA, and the magnetic flux density and the area of the coil where the flux density and area is normal to each other. You may be thinking, Miss, can I just write the equation? You can, but you got to define the terms. What is N? What is B? What is A? All right, so we don't have the mark scheme. I'm just guessing. So the product of number of turns in the coil and the magnetic flux density and the area of the coil is 1 mark, M1. And then the flux density is normal to each other. This is A1. Okay. Here we have a solenoid. Diameter and number of turns are given. Okay. And the variation time T with magnetic flux density is shown in figure. Okay. So now this is not current. This is B. Very nice. Okay. Calculate the maximum magnitude of the induced EMF. Oh, snap. So induced EMF is equal to the flux dt. We just want the magnitude, so I'm going to drop the negative sign. And if I find a negative sign, I'm also going to drop it. I need to adjust a bit. Back pain. Okay, find the induced EMF. So to find the flux dt, we'll start with this one. E is equal to the flux dt. But from my understanding, flux is equal to NBA. Correct? So if flux is NBA, then I can put inside E will be equal to d dt bracket NBA. All the constant we kick outside and we quarantine the variable. What is the variable? B. Area is constant because diameter is constant. N is constant because you didn't change the solenoid. So that would be N A dB dt. So if I want maximum magnitude, this means this is dB dt that is maximum. Where is dB dt maximum, my friends? Miss, here or here, this one. This is less steep, this is more steep. Very good. Okay, so we gotta find what dB dt is, which is the gradient. Okay, so from here, because it's 3 marks also, I'll write all the working clearly one. So I'm gonna then write that E is equal to NA multiplied by gradient of the graph, maximum gradient. Okay, draw a line. Let's find maximum gradient. So from here, gradient is equal to, I'm going to use the very obvious points here, 6, 250, and this is 7.2, 0. Okay, so 250 minus 0. Uh, 6 minus 7.2. So my gradient is, by the way, there's a milli here lah, the milli. Okay, let me put the milli here. Don't let the prefix cheat your feelings. That is not good. Okay, so by pressing calculator on the side, you will get the gradient as 0.208. Okay, if you want unit, then it's Tesla per second lah. Okay, we can substitute now. E will be equal to the number of turns. You go up there, number of turns is 540. Diameter is 6. Okay, so it's 540 multiply by area pi r square. So the radius is 3 times 10 to the power negative 2 square. Pi r square. And then the gradient, which is 0.208. You can find you press your calculator. This is 0.318 volt. So I'll put my answer here, 0.318. Okay, where do I think the 3 marks are? I think the 3 marks are, number 1, if you know how to find the correct gradient. I will call this C1. Okay, obviously the answer there is A1. And the answer A1 will come together with the right substitution. Okay, the next mark is when we see the flux dt and flux is NBA. This is C1. So you know how to start law. We start with Faraday's law, proportional or equal to d flux dt, and flux is equal to NBA. Somehow you define already NBA. So we're looking for this and the continuation. So somewhere here there is 1 mark 1. If they are nice, they will give you the mark here. If they are less nice, they will only give you the mark here. I think they are nice. Okay, so next part C. Let me drink some water. You read the question now. Okay, part C. A thin copper sheet X is supported on a rigid rod so that it hangs between the pole of the magnet. Sheet X is displaced to one side and then it oscillates. Ding, 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 ding. A motion sensor is used to record the displacement of X. So my X is going to swing in and out. Is there a change in flux in the copper sheet? Yes, changing area. Okay, so anyway, a second thin copper sheet replaces X. Sheet Y has the same dimension. The only difference is we cut little strips here, like a comb. Like a comb shape, you know, comb your hair, comb. All right. Motion sensor is again used to record the displacement. The graph in figure 9.5 shows the variation with time t of displacement of each of the copper sheet. Oh, okay. So there's one copper sheet where the amplitude, at least for the first 2 cycles, looks fairly constant. And then there's another oscillation or another sheet where it seems to be decreasing over time. Name the phenomena illustrated by the gradual reduction in amplitude of the dashed line, the green color one. Okay, this one is called loss in energy, right? It's called damping. 1 mark. Okay, so I think when I was reviewing chapter 13 with you, or you watched the chapter 13 oscillation review, I mentioned before oscillation can come together with damping, which will come together with induced EMF. Okay, deduce which copper sheet. So they want you to deduce. You know what is deduce in science? When you see the word deduce, deduce. Okay, let me ask my good friend Google. Hi Google, what is deduce? It says here, arrive at a conclusion by reasoning. So you need to reason out. Here lah. Arrive at a conclusion by reasoning. So you need to reason this out by looking at the evidence that is provided. So you want to know which copper sheet is represented by the dashed line. Explain your answer using principles of electromagnetic induction. Okay, so here is the template, the general template that you must modify if, let's say, you want to explain things using Faraday or Lenz law. Okay, so I'm going to paste the the one from your notes for you. So let me find them. A bit hang. Okay. So when we explain something using laws of electromagnetic induction, we will identify the cause and location of the change in flux. For example, the magnet moving inside the coil, or in this case, the copper sheet oscillating between the poles of the magnet. Okay. And then after that, we will relate it to Faraday's law. For example, EMF would be induced in the EMF will be induced in somewhere, don't know where lah. In this case, the EMF will be induced in the sheet law. So wherever there is a location, wherever there's a place where there's a change in flux, the EMF will be induced inside this place. Relate to the question, okay? So the magnetic flux will increase or decrease, and to oppose this change, describe what will happen to the system, and then talk about the energy conversion. So this is a general form or format. But now, right, you are asked to deduce or reason which one has a decrease in energy from mechanical to electric to heat. Okay, so I'm going to start with the evidence that I see, which is the dashed line. And also they are hinting for you to start there because they talk about damping. So type this out. Oh, big, so can see. So the dashed lines decrease in amplitude shows a loss in energy in the sheet in the form of heat. Okay, and then you can then mention this energy is derived from energy hence the sheet represented by the dashed line has a greater induced current. As the sheet oscillates the magnetic poles, the poles of the magnet. Okay, let me go and dig a bit. And the poles of the magnet. Ding, ding, ding. The current induced is greater in sheet X than Y. So sheet Y is the one with the cuts in between. So this is because the surface area is cut and are unable to cross the insulating air gaps or the insulating gaps between the strips. There is a smaller eddy current. Hence, sheet X, deduced represents the dash, or is represented by the dashed line. Okay, so I'm guessing that the mark scheme says the dashed line decrease in amplitude show that there's a loss in energy in the form of heat derived from the energy of oscillation. Here is 1 mark. Okay, that means you understand the idea that there is a decrease in energy, and it comes from the energy of oscillation and is dissipated as heat. There, mechanical, which is oscillation, that will eventually go to heat. Okay, in the form of heat. So you talk about the sheet represented by the dashed line has a greater induced current. 1 mark. Now I'm going to explain the origin of the induced current. Okay, so as the sheet oscillates between the magnets, okay, talk about there is a change in magnetic flux linkage or magnetic flux lah, according to and EMF is induced, or a current is induced. So the origin is here. When you explain, there is a change in magnetic flux in the sheet and EMF is induced. I'm not sure whether this one has marked because it's not really needed in the explanation, but who knows? Okay, I don't write the mark scheme today. And then next, the induced current is greater in sheet X because the surface current is X. Okay, hang on. There's smaller eddy current in Y. Okay, be specific lah. Okay, so if I am guessing, just a guess, that you say that the current induced is greater than X is enough already. You could say because the surface area is cut or the surface area is smaller because you cut out certain parts, right? So this one is 1 mark. But in case they want a bit more explanation, you say this law, electrons cannot cross the insulating gaps between the strip. So the eddy current cannot build up in Y. Okay, and then leading to the answer is 1 mark. Sheet X is represented by the dashed line. Yep. So that's it. This one is your FM21, which actually covers a lot, you see. There's analysis of the graph, there's calculation, there's explanation. The only difference is that they didn't ask you to sketch anything. So what we are talking about is we are identifying the cause and location of the flux. We are going reverse. There's an energy conversion, and then the greater energy conversion is with the greater surface area that is not cut. That's why the current is greater in X. So there's an energy conversion I explained in the red color point. Okay, so because there's a greater energy conversion, there's a greater electrical energy for the dashed line. So greater induced current. And then I talk about the law. And then I talk about how the current is greater in X because of the surface area being not cut. So the surface area. Okay, so just be a bit specific lah when you explain this. You may need to take some time to write out the explanation. Okay, so the current induced is greater in X than Y because the surface area of Y is cut or the surface area of X is uncut. Okay, and the electrons are unable to cross the insulating gaps between the strips. Okay, so if the mark scheme is linear, just you mentioning the current induced is greater in sheet X is good enough because it's all about rate of change in flux. So when the surface area is cut, area decrease, flux decrease, the flux dt decrease, EMF decrease. So everybody decrease. That's why there's a smaller eddy current in Y. So I tried to link this one here, which is understandable. You don't have space to write everything. Okay, so that's it. That's what I would suggest you write. That the dashed line shows a loss in energy in the form of heat. Great, the heat is from the energy of oscillation. So the dashed line should have a greater induced current. How do we know there's induced current and how do we know which induced current is bigger? There's induced current because from Faraday's law, when the sheet oscillates, there's a change in flux. However, the flux change in sheet X is bigger than sheet Y because Y, the surface area is cut and a bit extra, electrons cannot cross the insulating gap. So there's a smaller current in Y. So then you just deduce on sheet axis. Represented by a dashed line. All right, that's it. That's it. You're done with A2. So please go do past year. Regarding this, just make sure you do enough past year to cover all of these skills. Okay. Do some recent past year sets. All right. And also don't miss out on transformers. All right, that's it. If you're watching this video in last or wherever you're watching this video or whenever you're watching this video, stay calm, stay cool. You got this and just do your best. It's enough. All right. Take care and all the best in your papers. Goodbye.